also depressed at this point?
So let's actually go back in time and then look at the trades in the Stone Age. You know, someone, let's say, had a flint to start a fire, and then somebody else had, like, you know, an axe head, and basically they wanted to exchange it. Okay, so the exchange was kind of easy in that situation. We would just basically, there were no central authorities needed, like a bank or anything like that. So this was okay for a small community. They could just exchange the stuff that they wanted. But as the communities grow, we needed like a more complex system to do these transactions. People had, you know, communities had more needs, and basically they wanted something as a proxy to be able to trade with, as a medium of exchange, kind of. Okay, so basically what people did, they gradually found that metals, like for example gold, were a good medium of exchange, in the sense that these metals have properties that make them good enough as a currency, as a medium of exchange. For example, like gold specifically didn't have any intrinsic value back in that time. Like it was not used for any kind of cosmetic or any sort of like jewelry purposes. The reason that gold became a medium of exchange was the properties of gold. Like for example, it was scarce enough that, you know, people couldn't find it like everywhere. So it could be used as a currency, or it was like, it wouldn't rust, or it wouldn't like, basically gets melted easily or stuff like that. So there were certain properties in gold that made it a useful medium of exchange. But then back then, gold, so at some point, people figured out that there are also problems with metals. For example, they are not breakable. They cannot just break it into pieces, and then, you know, they can make it easy for the exchange. So they ended up with basically using, for example, paper money. I mean, it was invented in China at some point that, you know, you can use paper money to do the trades. Just want to give you an idea of like the history of it, so that you understand we don't necessarily need an intrinsic value in something to be able to trade it, okay? Or to be able to use it as a medium of exchange. Then, basically, gradually over time, governments and, you know, banks started to show up, and basically, like up until here, it was like communities that agree on a medium of exchange, for example, gold or some sort of stone or something else. They would do the exchange, but at some point, you know, things became more complex, and governments came to the picture, and then they basically, define the value of paper money, bank would get the valuables from the people, would give them the paper money, and then they will use that as the medium of exchange. Okay. Now, from almost a few decades ago, even paper money has become less popular. So we have, like, for example, credit cards and digital money that replace it. So what we have in bank cards is really digital money. It's just a series of zeros and ones, and just a number that balance that the bank keeps track of. And it also doesn't have any intrinsic value. The value is coming from the trust that we have in the bank, right? So we trust bank to keep track of the money that we have. It's just a digit or some balance that is kept somewhere. Right? So basically we have credit cards and digital money. And then these days cards are also gone, and we have like even cell phones. You can pay stuff, or you can just do it online. So you don't need really to have any physical things to do your trades, right? Now the bank model is called a centralized model, because bank is basically centrally controlling all the transactions and money transfer. So everyone is kind of trusting bank in this model. The question is, how can we basically remove the bank from the equation? Somehow build a system that doesn't rely on the bank, okay? And doesn't rely on any kind of trusted party or central trust model, which is like achieved through bank here. And this is where, like, we have all the, cryptocurrencies that came into the picture, and I'm gonna describe, like, basically how they work in this model. And I personally think that this is one of the, maybe, like, cryptocurrencies in general and blockchain and everything around it is one of the disruptive technologies in our age, because it enables us to do things that we couldn't do before. Now, in order to understand how a cryptocurrency works, let's first understand how a bank works to some extent and see, like, basically what we want to do. Let's think of like a transaction that you do on your cell phones. You pay for something on your mobile and you do a transaction. It's just code that is getting executed on your cell phone, right? It's just some piece of code that somebody has written and then it gets executed, right? When the money is something like physical, like paper or gold, you cannot duplicate it. I mean, let's make that assumption, because practically you cannot duplicate it. But when it's a piece of software, piece of code, you can just copy that code. And, basically, because your money is kept in terms of balances and digits, why can't you just copy the code and, double your, money in some way? The answer to this question is you cannot do that because the bank is keeping track of all your transactions and your money and your balance basically in a central place, right? So let's look at an example. In this case, Alice wants to do a transaction, to do transactions. What she can do, she can just open an account, identify herself to the bank, and then basically let's say that she wants to send 100 units of currency to Bob, and what he does, he just gets that money from the bank, by, for example, doing some work. You work for some company and you get, your salary or something, and then you send that money, let's say, to Bob to purchase something, and there is something like a ledger or think about it like a database that is kept on the bank side to keep track of all of these transactions. So the bank knows that Alice has like 100 balance, and then 10 units of it has been given to Bob, so the remaining balance is 90 in this case, right? So everyone trusts bank to keep an accurate record of all the transactions in this model, right? Now, so if you want to remove bank from this and make this decentralized, there are a couple of problems that need to be solved. So first thing is that note that everything is going to happen in code, so people can copy code, can copy your digits, and that could duplicate the currency that they have, for example, or they can impersonate someone else. So the problems that we have to solve here. We have the problem of ownership of the money and forgeability, someone forging basically who you're sending the money to, or how should the users connect and do the transactions, like, when we don't have a central place, where should the users connect to and do the transaction? And also the other problem is the double spending problem, how to make sure that people do not double spend the coins or the balance that they have. Okay, so these are the problems in short. And again, like, let's say you want to, think about an example. You want to design some sort of a, digital coin, and basically think of the digital coin as a string of bits, and then you have some code to run it. Let's say Alice wants to do a transaction to Bob. You have a function somewhere that returns your balance, like $50 that you have, let's say. And then you want to do a transaction, so you define a sender, sending an amount to a receiver. This is the code that you would write, right? Now the question is, running this code, what can prevent someone from changing Alice or impersonating Alice, to send some balance to themselves, because it's just a piece of code, right? The second problem is also that Alice, so this is an impersonation problem. The second problem is that Alice, for example, can double spend, can send the same amount of coin to two people at the same time, let's say. Okay? So these are the two problems that we want to somehow fix. And we already discussed that, the first problem also exists with the bank model because Alice needs to kind of show, her identity to the bank and prove that. And as they're doing a transaction, for example, they need to add a signature to their check, or they need to authenticate to the bank account that they have to be able to do that. And that authentication ensures that you cannot impersonate Alice, right? That problem is there in bank system, and it's solved with a signature of some sort, right? So we can basically do the same thing in this case let's say in a decentralized manner. We can still use something like a digital signature in this case. We can sign the transaction that Alice is doing. Let's say that's the piece of code, the parameters that you have to that function, to that transaction function. You are going to digitally sign those information, and then basically you're going to send it to Bob. So you're going to add a digital transaction, a digital signature to the transaction, right? Now, still, this doesn't prevent duplicating stuff. It prevents the impersonation, but it doesn't prevent duplication of, basically Alice can send the same signed thing to Bob multiple times, or Bob can actually do that, replay, the transactions multiple times, and nobody's going to be able to prevent that. So what can be done in this case? If you have any questions, please raise your hand. Can discuss it. What can be done in this case? So a question to you, what can be done in this case? You've seen this example multiple times. That what can be used to prevent replay attacks?
Create pairs of keys or something.
Sorry.
Set of keys for a person, for Bob it could be K1, K2, for the others it could be K2, K3.
For the freshness of a transaction, how would you do it?
Use an ID or something?
Some sort of an ID, or like a counter mode, like some sort of a counter, and if you see even the physical checks have some sort of a sequence number to them, right? So that sequence number is actually making sure that you cannot really repeat that. So basically, you add some sort of a serial number to it. So now the transaction looks like something like this. You add some sort of a number, an ID, let's say, to ensure the freshness of the thing, and then you sign it now, okay? So it's going to prevent the double spending in one-to-one setting. Like you want to send something to another person, you digitally sign it, and then you send it to them, right? So still, even with this solution, it doesn't solve the double spending problem that we had with Alice. Alice herself can still send the same coin to multiple people because it's just, it can just, Alice feels free to just sign anything that she wants and then send it to people. So she can, let's say Alice has a balance of 50. She's going to create different sequence numbers, and then it's going to sign the same message with a different sequence number and send it to different people. That doesn't prevent Alice from double spending. Now, the way that we solve this particular problem of double spending in bank is we have this ledger in bank that keeps track of the transactions. So that ledger ensures that Alice cannot just send the same money that she has to multiple people at the same time, let's say, right? Yeah. So in the setting of, so basically in the setting of, or in any kind of trading system that we have, we need to provide a way for two nodes. So we're going to solve that problem, but the first problem that we need to find a way for the nodes to talk to each other, like in any trading system. Like, for example, in the case of a bank, you have the bank that everyone is going to send what they want to do to the bank, and then the bank is going to, for example, perform the transaction for them, right? In a decentralized system, you also need, you need to be able to do that. You need to be able to find a way for the nodes to connect. So what is the solution in a decentralized manner to allow people to connect to each other? this is at the network level. Like they want to communicate at the network level to be able to just do the transaction together. Like I need to be able, like, let's say we want to have some sort of a decentralized cryptocurrency among ourselves. I should be able to communicate what I want to do with everyone here, right? How should I do that at the network level?
Put it in a central place and everybody can see that. So see the trace of that. So everything goes over.
But what is that central place? What can prevent people from going and changing that central place?
We can have, we can link them together so that if somebody changes something, and for before, everything else after that is invalid. So we can somehow change them together.
But let's step a bit, one step back. So how do you, like, we have nodes over the network, and then we want to connect them in a decentralized manner.
So everyone can keep a copy of a public ledger, and then they could just announce it and everyone else.
Yeah, so that's kind of what you said also. Everyone can keep track of a public ledger. Everyone is going to have a copy of it. But how can they send it to each other in a decentralized manner?
And send them to everybody.
Like how? Like what does everybody really means? Broadcasted, like how? It's this, like when we are talking about broadcasting, like in any network, like let's say, you want to communicate over internet, you should have some central place. Everyone sends messages to that place, and then that message is going to broadcast it to everyone. In a decentralized network, what is going to be that central place?
Some of the people are
I heard something.
Like P2P model. So
P2P. P2P model, like we had it before even Bitcoin, like, way back in 2000, we had Napster network or other networks that basically would operate in a P2P manner. There was no central server or anything to keep track of anything. Like everyone is going to connect to some network that is going to be tracked in a peer-to-peer manner, right? So that's the first step. That's the first step, that we need to design some sort of a peer-to-peer network, right? Now, in this visualization, I'm kind of, connecting everyone together. But in a peer-to-peer network, it's actually different. It's something like this. People are connected in a, like not everyone is connected to everyone. This is the centralized model. Like you have bank, everyone trusts this central place, so everyone is going to send messages, and this one is going to, for example, this node is going to say, I want to do a transaction with this one, so they're going to send a message to this central node. In a decentralized network, it's very essential to understand, like, this is like something that you need to understand before understanding like how blockchain works, and some of the problems that we have in blockchain is actually caused by this decentralized communication. Okay? We don't have access to something like this, and we don't have access to like every two node can connect to each other. We don't have such a thing because they don't even know each other like in the first place. So they need to somehow establish a P2P protocol so that they can communicate throughout the network, and every node can eventually gets added to the network at some point. The same way that peer-to-peer networks solve this problem of like node discovery and all of those stuff that I don't want to really talk. And we want to move the trust from this central place to the whole network, right? So that's what we want to do. Somehow move this trust from this central location to like every node in the network. And still enable any two parties to be able to connect and do a transaction. Now, let's look at an example. So the first step, as someone mentioned over there, was to ensure that everyone keeps track of the same ledger. Okay, so if you do, let's say, a node do a transaction with another node and then just add that transaction for themselves, that's not going to work, right? Because, the ledger that you have here is going to be different from the ledger over there, and so on and so forth, right? So you need to somehow unify these ledgers in some way, and this is decentralized still, right? You want to make sure that everyone is going to have the same ledger and keep track of like all the transactions there, right? And this should be done in a decentralized manner. We have a couple of problems in decentralized networks. And you know, in order to have the same ledger to agree on the same set of transactions, this is called the consensus algorithm. Like you need to come up with a consensus that the majority of the network come up with the same or agree on the same set of transactions. Okay, so and that's a big problem because the main thing is that you don't have established trust or a central place to do that, to establish that trust, and also you have the synchronization problem because over a peer-to-peer network the propagation time is very slow. It's slower than a central network because in a central network you're going to send it to one node and that's going to broadcast to everyone. In a peer-to-peer network there is some routing protocol and some latency in there, and it might enable like someone to cheat on the timing of things. Like I send a transaction to someone and I know that it's going to take 10 minutes or 5 minutes for that propagation to happen. I'm going to send the same transaction at the same time to someone else, and I'm going to cheat the network that way. So we need to solve these sort of problems, and it doesn't happen. And this has been discussed a lot. Like one of the projects that we have about the Byzantine protocols, consensus protocols, is actually going to bring us some examples of like those. Hopefully, that's a research project. But I'm going to give you a brief idea of like how blockchain and Bitcoin basically solve this problem. Now. Now let's say let's try an example here. Let's say this node here wants to send a transaction to the blue node, right? The red node wants to send a transaction to the blue node. What it does, it comes up. Let's say I want to send 20 units of currency to the other node. So what I'm going to do, I'm going to send a copy to everyone. Okay, I'm going to copy this transaction and send it to everyone over the network. It's going to take some time. That's fine. Let's just send it to everyone. And then this person is just want to make sure. Let's say you want to buy a pizza or something. They want to deliver the pizza back to you, and they want to make sure that the transaction has been confirmed by the network. Okay, so what they can do, everyone, like just a simple solution to this problem, everyone comes up with some sort of a token, something to confirm that they have received this transaction, and then they send it to that guy. And then once that guy receives enough of this confirmation, then he's going to say, okay, yeah, this is good. I'm going to send the pizza to the red node here, okay, to Bob basically, because I confirmed that everyone has that transaction. Now, what is the problem with this? Anyone can guess?
What if the dude who's receiving all the tokens isn't connected to anyone that the original person's
In a peer-to-peer network, there are solutions to solve that problem. There are intermediate nodes and routing protocols that you basically, if you want to send some packet to some other node, like when you're downloading something, for example, off one of these peer-to-peer network, you don't necessarily connect to the main node at the beginning. First, there is some protocol that establishes the connection between you two, and then you start doing the communication. So that should not be an issue. But there's another issue here.
The issue might be how long should it wait to receive all the tokens?
Let's say we wait like for enough time, and we find that what that enough time is.
Well, can there be issues with the timing? So if Red sends 2 transactions, and the first one gets accepted from another person really quick, and let's say that both transactions are all his money.
Yeah, that's a good one. Like this guy can send the same transaction. Can you repeat it again?
Yeah, so he can send the same transaction to 2 different people.
Yeah.
And then maybe while one's waiting to be accepted, another one gets accepted, and then perhaps they can both. Like just the timing.
Let's say we manage the timing in some way, in the sense that because this, the receiving guy, so the red node is going to ask everyone to send the confirmation to the receiver node, right?
Yes, so even if it does that, then other people might be confirming transactions and it doesn't happen too. So if he sends the 2, and then one of them gets rejected, then all these other people might have already kind of confirmed that transaction. So like you have to tell people.
Oh yeah. I agree. Like if the transaction, like that guy should also send back some notification to everyone that whether the transaction actually happened or not. Yeah, that's a good point. That's one point actually, but there is a bigger problem here. Ali, do you want to?
It was lost in the question. I don't know exactly
The question is, this guy wants to make sure, or the receiving, the blue node wants to make sure that this transaction has actually been confirmed by the network. Everyone in the network. So everyone has sent their token to the receiving guy. So the receiving guy can confirm if it receives enough of these tokens. And if so, then it's going to confirm and it's going to send the pizza back to the red node.
Okay, so you want to confirm that how much is enough?
No, I want to say, like, let's say we agree on that in some way, and that part is okay, but there's still a bigger problem. Let's say you agree on, like, the network size is like 100, and if 60 people send you enough tokens, then we're going to accept it. We say, okay, that's fine. It's going to work. What's the problem there?
You can have control of other nodes and add other nodes to the network.
Yep. That's the main problem that is going to happen. So what's going to happen is that, so this is going to be an adversary, let's say, and wants to cheat. So what's going to do, it's going to create a bunch of sock puppet accounts. You know, it's a peer-to-peer network. You can just do whatever you want. You can just create, like, it's a computer program. You can just create as many you want, right? You can create nodes. And then this is called a Sybil attack, basically, for these sort of, like, protocols. And what they can do, they can say, okay, if you need 60 confirmations among, like, 100, I'm going to create 60 accounts myself. I'm going to ignore the whole network, and I'm going to send the transaction to them. They're going to create one big token, or everyone is going to create their own token, and they're going to send it to that guy, and that guy is going to send the pizza to this person. So you're going to be able to cheat, right?
So everybody should only be able to send the token once. That's the point.
Yeah. I mean, you know, we ensure that happen. Those things we can solve them with the stuff that we learned in the class. That you send it only once. You know, for example, like we can make sure that freshness is there. But you know, it doesn't matter because you can create as many accounts as you want. So it doesn't really. Still, you're gonna be able to break this protocol. Now, this is why we have proof of work. Proof of work, you've heard it probably. You've heard the name. Is a way for the network to make it costly for people to confirm a transaction, to make it costly for you to just create accounts. It doesn't matter, yeah, you can create accounts, but you need to pay a cost if you want to actually send that token. So not everyone could afford, you know, sending that, you know, cost that I'm going to define, and that cost could be in different ways. So the way, and this is called like proof of work. Basically, we need every node to do a computation that needs adjustable energy and time. So you need to spend some energy, some time to be able to do the computation. Okay? And the way that it's constructed is like, let's say, you know, we have some sort of a transaction representation here, and then, you know, you need to find, basically, you define a target. Let's say the hash function is, the output of the hash function is numerical. You just require that the output is less than a target, okay? So if you have a hash function that is, let's say, 128 bits, this target is going to define how many attempts you need to make in order to achieve that target, right? You know, it's not going to, you don't need to find a collision or something. You just need to find one output of the hash function that is less than this target. And the way that you do it, you're going to increment some counter. That's basically, you're going to increment that counter, find the number that if you add it to this block, you're going to be less than that target. And then this is like the proof that you've done this computation. Okay? So you're going to basically using the hash function in a way that, you know, make it like, you can kind of adjust it with this target, how hard this problem is going to be to solve. Because, for example, if you put the value 2 here, it's going to be extremely hard because you need to find an input to the hash function that the output is actually 1 or 0, right? But if you make this target, let's say 2 to the power of 64, with a high chance, like basically it's going to be very easy then. Because, you know, almost like, maybe 264 is not that easy yet. But let's say 128 bits of output, you can set this to, let's say, 120. You know, it's still going to be, you know, manageable. They can find this counter relatively fast. So if you play around with this target, you can make this problem, this computation, hard or easy. right? So you can adjust. And actually in Bitcoin, you can estimate, based on the computation power of the network, you can estimate what target to set so that you require around 10 minutes for it to be solved in the network, based on the power that people have. So that's basically the reason for, so now if you go back, if it's a hard problem that needs to be solved by every node, then if you create 100 accounts, it doesn't matter still, because you need to do that computation for every token that you want to send back, right? So it's going to be really hard. Yeah.
I was just a bit confused on the incrementing for that. So how come you're incrementing before hashing to make it harder?
No, you increment and after you basically do an exhaustive search for this counter, the right counter, such that the hash of the block plus the hash, the counter is less than the target.
So the counter's not within the hash.
No, it's is inside the hash.
I guess before you hash the value, you add the counter.
Yeah. So you add so this is the block that you want to certify that you have actually done a computation. You add the counter to it, and then you hash it, and then it should be less than the target. And you repeatedly do this, like for every counter, like let's say you tried with 1, 2, 3, 4, and so on and so forth, and then you hash it, and then it should be less than the target.
If the counter goes up, it becomes harder to hit that target.
If the target goes up, if the target goes down, then it becomes, the lower the target, the harder the computation is. Because, you know, like if you pick, like, let's say 200, yeah.
The counter is just a random number?
Yeah, just a random number. I mean, you don't need to, like, you know, the requirement for a hash function is that you want to make sure that people need to do an exhaustive search here, right? Like, they cannot just cheat and find, like, that number mathematically, like, by just for calculating something and then, or do it in, like, 1 minute rather than 10 minutes, something like that, okay? So and a hash function actually provides that. Like, I think, like, if you, for example, have, like, SHA-256 here, for example, that's going to be the case. So if you can break SHA-256, you're going to be very wealthy, you know, because you can break the proof of work. Yeah, is the difficulty level. So the target defines the difficulty level. Yeah. Now, let's see how it works. Now, this guy wants to send a transaction to that person, so they're going to create the transaction. They're going to send it to everyone. And then everyone is going to try to do the proof of work now. So everyone is going to start, you know, doing a loop on that counter and finding the right one. And then, let's say, that particular node finds it, and then is going to send the confirmation, and we're going to, you know, I'm not going to go into details what that confirmation is, but think about it this way: if you find that counter, and you know everyone knows the transaction that you're doing, so it's just basically the receiving node can verify that you've actually done the computation, right? It's called, like this process called mining, yeah. Yeah, is the mining process basically that you've heard. And then, you know, you're going to accept the transaction, right? Now, what is going to be the problem still?
What is the incentive for others to actually do the
Yeah, that's a very good question. The incentive is the extra, like in Bitcoin particularly, if you finalize a transaction, you're going to get a transaction fee or something like that. So this is actually the mining process that your friend said, you know, as part of the mining, you're going to get some reward in terms of like Bitcoin.
So to keep all those history of transactions in synchrony, everyone should do the computation, right? So if someone has a low power computation, low power computer, how can they keep up with the network?
So not like in the actual, you know, in the real world, like you can have a wallet and you don't need to do any computations necessarily. It's like only people that are interested in that reward and have enough power, they're going to actually do the computation. And because there's a reward, you know, it's actually a very nice, like this is a very good question in the sense that if you actually think about it, The whole economy around Bitcoin is actually because of that. Like, you need to adjust the reward that you give to the node so that it makes sense for them, like, because they're paying for electricity and energy. You need to make that reward even adjustable in a way that you make Bitcoin scarce enough that becomes valuable, and at the same time rewarding enough for these people to do the computation. So it's like, it serves a multiple purposes here, like this single proof of, like, this is the core of Bitcoin, the mining process, because it kind of, manages the economy of Bitcoin, keep the scarcity of the currency in the Bitcoin, and at the same time, make sure that you reward the people that are doing the computation. Does that answer your question?
My first question is that the random numbers that the blue node gets should be different. So
Which random number?
just proof of working.
The counter?
Yeah.
The counter is just a value.
Because I mean that if it's not like that.
No, the transaction block itself is going to be different every time.
No, in one transaction, for example, one of the nodes finds the counter that works,
Yeah.
and it sends it to the others, and they all send it to the blue node, and he or she will think that there are a lot of tokens, but
Yeah.
maybe just one.
No, in this proof of work, there's only one token. And the token is sent by the person that did by the node that did the calculation. One token. But it's a proof that they've actually done the calculation.
So that means the incentive for those people to approve the token is that they can, through the mining process, they can get new Bitcoin. Is it?
Yeah. The mining process ensures that you keep some reward. And this is how Bitcoin inventory kind of increases over time.
And just curious to know. So what is the, like, my understanding about Bitcoin is like it's a mathematical computation. Or you can correct me if I'm wrong. So that means the mining process is you use the computing power to compute, like, based on some formula.
That hash function. Yeah.
Formulas to,
Yeah. The hash function that I showed, yeah.
to get the value which is
The correct one.
the correct one.
Yeah. That's exactly it. Basically, you want to make it costly for nodes that, they cannot just simply add nodes because there's some computation involved.
How does it stop them from just making another sock puppet if it's computable at once?
Say it again, sorry.
How does it stop them from just making another user?
Another account?
Yeah.
They can still do it.
Yeah, and then they verify that it's still like a faulty.
That's actually the next slide.
Here, for the people who do the computation, they receive this transaction fee.
Yeah.
It's kind of the money that is given to them out of nowhere.
Yeah.
Does it?
It's out of nowhere because they did the computation.
But
It's a reward.
yeah, okay. Let's say a pizza costs $20.
Yeah.
And after, I don't know, 20 years, many people get those transaction fees. That doesn't it kind of impact the actual value of the money?
As long as it's, like, first of all, the reward is adjustable over time. It's going to be decided by the network. It's part of the consensus algorithm. The target itself is part of the consensus algorithm. You come up, like, the whole network agrees on a target and agrees on a reward. That, we are going to give this much reward to the people. And it's going to actually decrease over time to make sure, like, the scarcity of the money and, the economy of it. Yeah.
But actually my understanding is there is a limit of the total number of
Yeah, there's a limit, yeah, there's a limit. And it's going to be, it's not going to be infinite. But it's still, there are going to be transaction fees and the other mechanisms to move after that point. Yeah.
I think the problem of this scheme is that some group has the more computational power.
Yeah.
And the others, they can do double spend.
Yeah, I'm going to describe that, exactly. I'm going to explain that, yeah. So a problem still exists here. You can just, let's say you want to do a transaction, just create, let's say, now a smaller number of nodes, and you're going to send the transaction only to the nodes that you own, not everyone else. So nobody is aware of it. And they're going to start doing the proof of work or the mining process. they're going to eventually solve it. Nobody is aware of this. And they're going to send the confirmation, and the receiving poor guy is going to believe it, right? And then they're going to give you the pizza, right? That's still a problem. Because the network should be aware of these transactions somehow, right? Now, that's the next part that we need to basically, first, we need to chain stuff to make sure that, you know, the transactions are basically, the transactions are connected. So basically every transaction depends or is, let's think about it as a hash of the previous transaction, and you chain them this way. So this chaining mechanism is gonna help us prevent this new problem that we talked about, okay? So the way that we chain them is something like this. You know, every block is gonna depend, or let's say hash of the previous block, and future, like you're gonna also get a hash of the future, the next block, and you're gonna add it to somehow, like a link, like a double linked list or something like that. You know, so you're gonna chain these blocks like that. Now, this provides something that is called immutability of the blockchain, in the sense that let's say somehow you found a way to make a modification to one of the blocks. That's not going to help you, because this chaining process is going to ensure that, you know, this guy has the hash of the previous one. So if you change that one, you need to compute a hash, like a collision for the hash, for example, to be able to do it, right? So this chaining is going to give us immutability. But let's see how it actually helps us solve that problem. Now, let's say we start from a block, and in Bitcoin, specifically, blocks are generated every 10 minutes, okay? And then we go for the next block, and then a bunch of bad nodes, sock puppets, start showing up. So what they do, the way that I explained to you, they just create a new block by just communicating to themselves. The rest of the network is not aware of this particular block. So the rest of the network is processing other transactions, okay? So basically, they just do their own transaction. So from here, the network is not synchronized anymore. There are two copies of the blockchain, one for the bad guys, one for the rest of the network. And they continue this way. They add a block, the next block, and then the good guys are going to do that. And then this is going to go on. But, you know, because the computation power, the assumption in blockchain is that the computational power of the bad guys, or basically at least 50% of the nodes, or the computational power that we have in the nodes, should belong to the honest parties. With that assumption, they cannot keep up with this process. At some point, the whole network is gonna be able to generate more, like the longest path or the longest branch in the blockchain. Okay, so, and then the thing that the network, what it's going to do is going to accept the longest sequence of blocks. As you're doing this, let's say a bunch of bad nodes want to fool another node in the network. That node is going to immediately, immediately detect that something is wrong, because they're going to see a branch. They're going to see two sequences of transactions. Two, like the red one that it doesn't know if it's valid or not, and the gray one. So it's going to hold off and wait for the network to see which of these sequences is going to run longer. As soon as, like, basically the client is going to confirm. So if you want to do a real transaction, let's say in a Bitcoin, and something like this happens, then the client is going to hold off not validating the transaction until it figures out which one is going to be the longer sequence. Maybe these nodes can do the computations every 10 minutes or so for a couple of times, being lucky, but they cannot do it like the rest of the network. So at some point, eventually, the longest running sequence is going to win, and the other one is going to be rejected. Okay? I think we reached probably this point last time. Now, one thing is, like the transactions that I showed earlier, it was just one transaction, okay? And I also said, like, every 10, like Bitcoin basically generates these blocks every 10 minutes, because the computation is going to take some time, right? that computation is adjusted so that it can be solved by the network every 10 minutes or so, right? So if you want to do one transaction per 10 minutes, that's going to be very bad, right? Because it's very slow. Like, you cannot do real world transactions. It's not really going to work. So we need a solution for this. We need to be able to do a lot more number of transactions per, let's say, every 10 minutes. In real-world applications, like when you do bank transactions, massive number of transactions happen at the same time, like in seconds, right? So we want some sort of a way, some way to support that in blockchain as well, so that we can increase the rate of transactions, right? And actually, like each block of transaction is not just a single transaction; is a number of is a collection of transactions. Okay, so basically every time that you want to do a transaction, let's say like 10 nodes in the network want to do a transaction. What they're going to do, they're going to announce this. They want to do this transaction. They're going to announce it to the network. So a block is going to be created. So a block is just a collection of transactions together, which each one is signed by the particular parties involved and whatnot. Okay, and then this whole block needs to be validated. Okay, this is why it's not is called a block, because it's a set of transactions. It's not just one. So this needs to be validated, right? In order to be validated, then the proof of work and the mining process actually happens. Okay, does that make sense? So instead of like having one, we have a set of transactions together that form a block. Now, there is this concept of Merkle tree that is used to combine basically these transactions to put them into blocks, so that we ensure that like basically the client. So there's a problem in terms of if the client wants to really confirm a block of transactions, it needs to make sure that all of those connections to the previous blocks and whatnot is actually valid, right? It needs to check a few things, right? Let's say you just try to connect to the network now, and you want to just validate the transactions. It's going to be massive number of transactions that you need to validate. So it's going to be very impractical if you want to validate all of them. What you do here is you basically think about it this way. You're going to combine, you're going to basically instead of like taking a hash of all of the individual transactions, you're going to, you want some sort of a structure to calculate the checksum of the transaction in such a way that it can be easily, these are the conditions actually, it can be, make it efficient to check. You want to make sure that the content of the block does not change, so it's some sort of authenticate or checksum to be added for each block, and also you want to preserve the order of the transactions. Okay, so you want to make sure that the order of the transactions are also valid, because the order could the order of the transactions could also be something that people can manipulate maybe to gain something. For example, if these transactions happened before that one, maybe they can do something with it, right? So in order to ensure all of this stuff happens, there is this concept of Merkle tree, which is basically, think about it this way, if you want to hash this block, create some sort of a checksum of it, you're going to hash each individual one, and then you're going to basically combine the hashes of two of them, and then combine the hashes of the other two, and then you're going to combine the hashes of the final things. So it's like some sort of a tree structure of hashing things together so that you preserve the order and you make sure that the content doesn't change. So that would give you maybe the starting, the basic idea of how a blockchain works. Now, there are a couple of things that is good to understand how blockchains or cryptocurrencies work. I've kind of put it into appendix, but for the proof of work, there are other options that people could do. So proof of work is works based on computation. Like you have computation you do the computation. Let's say you have some, I don't know, piece of hardware that can do the computation for you. The ownership of that piece of hardware and the time that you spend on it is the proof that you're actually using to validate transactions. Now, there are other things that you could build. You could, for example, like build a hard problem that needs storage to be solved, to be able to solve a problem within some amount of time. Not necessarily just spending time on it. It's more like you need this much storage to be able to solve the hard problem. So you can have something like a proof of a storage, like a proof that you have some storage available. And the assumption, again, in such a network is that, you know, a bad entity cannot have more storage than more than 50% of the network, something like that. The other one that is also famous is the proof of a stake. Basically, in proof of a stake, depending on how much value units of the currency that you have, you somehow get you can bid on the transactions to validate them. It's just that. Basically, depending on how much of the currency, the units of the currency you have, you can just bid on validating a transaction. So it's basically proof of how much you have at the stake, how much you want to put at the stake. From like basically this forces the people that want to validate the transactions make sure that they're actually putting something from the value that they have at the stake to validate the transaction. So they should be very careful not to validate transactions that are bad, something like that. So it kind of enforces, you know, people the nodes in the network to be careful when they're validating nodes, right? Validating transactions or blocks. So that's how proof of stake works. And we have, again, as I said, we have proof of space, proof of storage, proof of space-time. We have different, you know, you can think of different, different type of these computational hard problems, consensus algorithms that would make sure that the nodes in the network own something. They have something that they put at the stake to be able to, you know, so that other nodes cannot just create accounts for free, you know, something like that. Any questions so far? No. So this is like basically once, let's say you connect to a network, you're going to download the whole blockchain, which is like basically the chain of these blocks, right? You're going to download all of them, including all the hashes. Okay? So you're going to start validating them back in time. So you're going to go back in time and validate them. Now, if you want to add a new block, then that's the time that you are going to calculate, you know, the proof of work or whatever, and then you're going to include it in your proof, in your, as a validation of the block, with the block itself, and you're going to send it to the network, basically, or to the receiving node.
Sending it to network, you should send it to everyone, yeah? And,
once I'm not sure exactly about this, but once the receiving node is going to confirm this, then basically, yes, it's propagated into the whole network so that everyone adds it to their own blockchain.
I just think that if some different people find the hash for one block, who is deciding that which block should be accepted?
This is what I explained in the previous, you know, this case here. Is that cover? Like, does that answer your question, or is it a different?
I just think that they're not adversaries. They are just normal.
Oh, like let's say two people at the same time do it.
Yeah, not at the same time, but with some time difference. And who is deciding that which one should be accepted? Because there's a network, and it should be sent to everyone. For example, I send it to this hub first, and the other one send it to that hub.
So assuming that there are honest players, we have, let's say we have over like some percent of the network or there are honest nodes. These kind of consensus algorithms exist that, you know, you can, like a whole network can agree on let's say they want to compute something. It doesn't matter. It doesn't need to be like just basically this is a computation. Computation of, like, the computation is like accepting a block, right? Accepting a block is like saying yes, you're computing a yes, right? That this block is valid. So those consensus algorithms are going to take care of it as a network. And you basically, the way that, you can think of it is like, the clients are going to accept the one that has the highest rate first, something like that. Like they receive like so many nodes are going to receive the same value first, something like that. Yeah, it's just a normal consensus algorithm. Yeah, but there might be like this case that I explained here is not going to be covered by normal consensus algorithm in this particular application. So we needed to kind of think about it and solve it, and basically proof of work combined with the chaining of the blocks is going to solve that problem. Now, the other thing, these are just a few slides just explaining some of the other concepts, okay? If you remember, I defined the transaction to be some sort of a code. You're executing like sending some amount to the receiver, right? That was basically some code that we called like a transaction, right? Transaction is actually code. It's not, so it could be like, you can think of it this way. It's a piece of code that is going to be executed by the clients, right? To actually say that the transaction was valid, right? And then everybody adds the transactions to their blockchain, right? It's some sort of code that executes. Now, you can change that code. You can customize that code to some extent, right? You can make it do things that you want, right? Basically, you can write a script there. It doesn't necessarily need to be just this template that I showed here, a sender sending some amount to a receiver. It could be customized, right? And there are a bunch of things that you could do this. Like there are so many things that you could do this. For example, you can add a timing factor to a transaction. Like it should happen at a particular time, let's say, right? And then you can add it here. Like sender sends this amount to the receiver at this particular time, something like that. Or you can make it conditional, right? You can make it make this code conditional, like add an if statement or some sort of condition. Or you can add a score to it, or you can make it a contract, some sort of a contract, okay? And that's how smart contracts. This is the concept of a smart contract. Basically, you're just saying, okay, this transaction code could be customized in different ways, right? So I customize it by adding a condition or a time to it or whatnot. And there are some, like basically Bitcoin has this scripting language that you could actually custom, which is very hard to work with. And this is why like some of the newer cryptocurrencies added more, like made it easier to actually, made it easier to define different types of smart contracts. And we have a group that actually have worked on these smart contracts, so they're going to present more. But the nice thing about it is that if you create a blockchain and you have this capability of customizing transactions, you can actually create another cryptocurrency within a blockchain. So if you create one blockchain, you can add a bunch of, you can just create as like many other sub-cryptocurrencies kind of say, let's say, to it, which is basically the concept of like, let's say, tokens, right? Because what you can do, like, let's say you have this, right? You can create some sort of imaginary, like just name some sort of a, let's say, coin, let's say, it's called token, basically. You can just give it a name, let's say, I don't know, ABC token, and then you can say, okay, I'm sending these many ABCs to this other person in the network, right? And putting it in one blockchain. So you're creating one blockchain, but you can add as many of these tokens as you want to it, because you can customize this transaction. You can say, okay, add this particular token to, or send this particular token to someone else, or ABC, I don't know, any variations. You can create like just names, and then kind of creating a cryptocurrency within or inside a blockchain.
But like in the previous case, as the adversary was sending it to all the parties, if the adversary is doing it, they will know about all the conditions that has been mentioned.
Yeah, yeah. The conditions are going to be publicly available. People can check it, and this is the nice thing about it. Everyone in the network can check the condition. Like, let's say you want to buy a pizza, just within this time. Let's say, then the transaction is going to execute at that time, and then you're going to get it at a particular time. So the condition is actually public to everyone. So they can, and this is why the client can validate and can execute it within the condition that you have defined. And this is, you can think of this thing as a condition that within the blockchain, you're going to say, send this particular token. And this token is something like kind of imaginary. It's not like, you can just create the backend for a blockchain, and then you can have like many cryptocurrencies or many tokens defined under that blockchain as a condition of it, some sort of customization of the transactions.
So this way, are we making transactions token dependent?
No, this is actually we are making it token independent, because you can define any token on it. You can we have the like Ethereum network is one blockchain, is an implementation of blockchain, but there's so many tokens that you can define under Ethereum by just using this trick that you can define just the token name, and then you can say, okay, send this transaction of this kind to these people, to sort of sub part of the network, something like that. Make sense? Now, a couple of things, how to hack Bitcoin. There are a couple of ways that you can hack Bitcoin. The first one, obvious one, is 51% attack. So if you have a lot of computation, let's say, I don't know, a nation state or Google or someone can actually hack Bitcoin, can add transactions because they have a lot of computation in hand, right? And you can also, there are also like basically these mining pools, the concept of mining pool, which basically is like people get together, they create a pool of nodes, and then each one contributes some computation that they have, let's say their own PC or something, it's a piece of hardware to it, and then they try to solve that computational problem, that mining, that proof of work problem together, like parallelizing the computation together and trying to solving it, right? So they could do this, right? And there are a bunch of these pools that people, like for example for Bitcoin and others, people have created so that they can mine Bitcoin together, okay? And now the problem is, let me see actually if I have another, yeah, I think I don't have it. I'm going to explain to you. So the problem here is that what if one of these, pools grow large enough to be more than 50%? Then they can actually break, they can break because they have now more computation than the rest of the network, and it's kind of one entity. And actually this happened. This happened once for Bitcoin, that, a pool that people created together grew larger than the net, like larger than 50%, for a short period of time. And then they agreed that, yeah, they shouldn't do this, and they reduced it, they break it down, and they basically agreed not to go over, the limit. And now that particular Bitcoin pool is actually maybe 2-3% of the computational power of like the pool size of, or the ratio within Bitcoin right now. So it's actually, and there is a way to solve this problem as well, and I'm going to talk about it a bit more, after this thing. Now, the other way is to break the cryptographic, algorithms that we use there, right? So, for example, like quantum computers may come and then they can break some of maybe they can break the digital signature part, they can break other stuff, and then what happens then? Or maybe even like some of the algorithms that we are using now without quantum computers, maybe someone can break them. Or maybe there is a bug in the client that allows an attack. What should we do in those cases? People can attack it, right? What could be the solution? What do you think? Now, the solution is like for ordinary like peer-to-peer networks, if there's a bug in the client, or they want to change the protocol in some way, they want to add a new crypto, let's say, algorithm to it, What they do is just they release a new client, a new version of the client. And then everybody in the network, they're going to agree, they're going to download that new version. And some of the changes are minor, so it doesn't matter if you update or not. But some of the changes are major, so in the sense that if you don't update your client, you're not going to be synced with the rest of the network. And you're going to basically, the client is not going to work with the rest of the network. So they are going to create a new version of the client, and everyone agrees to download that new version. Now, what is going to happen next is this concept of forking, okay? The forking is basically, think about it this way. Something happens. It could be someone breaking the crypto algorithms, or client has a bug or vulnerability or any other reason. They say, okay, at this particular block or at this particular location, at some point, we're going to release a new version of the client, and that new version of the client is going to solve the problem. And everybody is going to jump on the new version of the client to make sure that this problem gets solved. So if you want to add a new cryptographic algorithms or change the consensus algorithm or whatnot, you can do that. You can just create a fork, which basically means that if you stay on the older version of the client, you don't update your client, you may end up creating a fork of the blockchain. The blockchain itself is going to be forked with the older version of the client, and the newer version of the client is going to actually create another branch because they're not going to be synced, right? Because they're changing stuff in there. And if everyone agrees to follow what everyone, like the network agreed, then it's going to be fine. We don't care about the other branch because it's like most people have upgraded, right?
How quantum computers can actually be used to hack Bitcoin? Like, is it the hashing time which will be reduced? And if so, then all the clients are like normal computers. So even if there is a new version, like the quantum computers will outperform whatever there is.
Yeah.
So is this version also valid there?
Yeah. So quantum computers can break, like, let's say, the digital signature that we're using RSA, for example. They can solve the factorization problem, or they can, let's say, speed up the hashing computation. But still, there are crypto-safe algorithms that we can bring in, and this is like releasing a new version of the Bitcoin client with those more advanced like algorithms, let's say. So that's going to solve the problem for future, right? Now, going past, like, let's say a quantum computer tries to modify stuff back in time, and then still it's going to probably take a lot of time for a quantum computer to be able to do all the calculations. A quantum computer is not going to work like an exponential, like cannot solve exponential problems still. It's going to be, in terms of complexity classes, if you know it, it's like, it's still overlapping with polynomial class, but it's still not solving some of the exponential ones, right? So it's going to take some time. Like, it's going to improve the running time of the algorithms by, like, let's say, I don't remember exactly, but it's not going to be significant. It's going to be significant for some of the, like, factorization is going to be significant. It's going to be from sub-polynomial to like a large polynomial type algorithm, but still it's going to take it a long time to calculate all the hashes and putting pieces together. So it's going to provide some protection. I'm not saying like it's going to be quite... The other thing that could... let me see if I have... the other thing that you could potentially do with a forking is, let's say somebody hacked an account, a wallet or of somebody, and then they could steal a lot of money, a lot of Bitcoins, let's say. We could potentially, if the whole community agrees to do it, create a fork and then remove that part of the blockchain that basically had that invalid transaction or malicious transaction. But everybody should agree. Like, if they steal like a couple of Bitcoins here and there, it doesn't make sense for people to agree to just, fork the whole blockchain. But if it's significant, and actually, I don't remember which one, but in one of the cryptocurrencies, a huge hack happened, and then people agree that, okay, maybe we should just fork, and then with that fork, we're going to basically you know, let's say this part is the malicious transaction, we're going to ignore it, we're going to remove that one and then continue from here. And basically they return the money back to the person that owned it. So forking can also like prevent those kind of, I mean not prevent, provide a solution if the whole community agrees to do this. Not necessarily the case for a small number of Bitcoins or cryptocurrency units here and there.
How is forking like agreed upon and initiated?
Typically, maybe a good example of this, I don't know if I have a slide for it. Yeah, maybe I have, yeah. So typically, this is like the history of forks for Bitcoin. But like we have, for example, Bitcoin Cash, Bitcoin Gold, if you've heard about them. But the way it works is like these are community-based. People actually are active in forums discussing stuff, like the more technical people that understand these things discuss this, and then they come up with some sort of a consensus in the community that, oh, I want to make this change to, let's say, Bitcoin. I want to do this particular thing and create a fork of Bitcoin. And then most of the cases, I don't know, most or whatever. So if enough people agree to do that, then it's just, you can yourself, like you can go and change the Bitcoin client. And if you have enough number of people agreeing with you for the change, then you're going to create your own community, and then you're going to create a fork of Bitcoin, and you're going to basically own that. You know, you can do it yourself. But it's like, if you do it yourself and you just follow it yourself, it doesn't make sense because you want to do transactions. So these are the big ones, you know, like Bitcoin Cash. Some people thought that, you know, we should have this kind of protocol in there, and then they had a good community around them, and they create a fork of Bitcoin. So Bitcoin forks is quite community-based. Like if you can come up with a good community around yourself, you can create a fork of it, or you can create your own cryptocurrency. You see that the economy of Bitcoin is working with that community, okay, around it, yeah.
For Bitcoin itself, is there anyone that's maintains the code? I mean,
Yeah. Yeah, all the codes are maintained actually by an active community. So initially it was created by the original owner. Yeah, but then nowadays it's an active community that is developing Bitcoin client. Yeah. So in the early days, like if you go back, like when it was created, he sends like a bunch of emails to people and then say, oh, I have this, and then people got interested, and then a community was formed around it, and then the more active people took the ownership, and he basically stopped doing any activity. And then it's been like that. And again, like you can go and change the Bitcoin client for yourself. It's like if you have enough people that follow you and you have like a voice in the community, that's good. That's gonna work. But if it's only a single person or two people creating a branch, nobody's gonna care about them. And there are other type of hacks, like hacking the smart contracts. For example, logical bugs in the smart contract code, hacking the wallet, like stealing the private key. Hacking the web services like the online wallets or you know, fraudulent crypto exchanges like Quadriga, if you've heard about it. There are things that has happened. You can search each one of them. There is a nice Netflix documentary about this one. If you want to watch it, it's pretty kind of cool what the guy did. Now, the question is Bitcoin really decentralized? Yeah, that's kind of what you expect, right? It's actually built to be decentralized, right? The technology is actually decentralized in the sense that the way that I explained it, there's a community around it, everyone is going to agree on some protocol, and then they're going to do it, and then if more than 50% of it is honest nodes, then it's going to work. Now, the problem is the economy of it. The economy of it is not actually decentralized in this fashion. This is, I don't know if you know the technical details, but basically think about it this way. This is the percentage of, if I'm correct, the percentage of Bitcoins that is owned by what percentage of the population. So if you heard like 80% of the wealth is owned by 20% of people, something like that, this is a curve that kind of shows like what percentage of it is owned by what percentage of people in the community. The problem is for Bitcoin is like this is, if you want to compare it to a real world economy, this is how a normal graph works. Like it's somewhere around here, okay? For Bitcoin, the wealth distribution is quite centralized in the sense that a small number of people, I think maybe around 1,000 people or so, own over 95, 98%, 90 something percent of the Bitcoin. So this is why the fluctuations are there. Like those people, if they make some transactions or some news come out, something happens, people are gonna, get concerned, and then they're gonna, the economy is not decentralized enough so that, these fluctuations, the fluctuations in the price of Bitcoin doesn't happen. So it's really bad from that perspective, Bitcoin itself. There are other cryptocurrencies that might be a bit better, but typically this is a problem with cryptocurrencies right now. Major number of like the coins are owned, or close to 100% of the coins are owned by a small number of people, and most people have only like a couple of Bitcoins here and there, or even less than a Bitcoin. This is the actual like distribution. If you wanna actually like you can look it up. This is older. I got it like a long time ago, but probably it's still the same. That only 85 people, if I'm correct to interpret this, have 13% or something like that. Yeah. Actually, more than that. I forgot like how to read this, but it was like 85 people I think have 13% of it, I guess. Anyway, that graph that I had would base. Oh yeah, here's the thing. I think only 0.35% owns 85% of the economy of the Bitcoins. So these are the actual numbers. So it's pretty bad from that perspective. And I think it's not good for investment exactly because of this fact. Okay, it's a nice I love the technology, and I think it's gonna work in the future. It's gonna bring a lot of stuff. Maybe nowadays it's used by I don't know, to get ransom or other stuff now, but I think in future, similar to a lot of the decentralized technologies that we have now, I think it's gonna be a thing. Like for example, Wikipedia is a decentralized thing, right? It's so powerful because of that decentralization.
I think that, for the government, like it's so volatile. I think it's a good idea. Always you can do pretty small transactions for every coin, so you always win a little bit, and you always win an amount of.
Yeah, I understand there are techniques that you could take advantage of Bitcoin for sure. I'm just saying for normal people that don't understand like how to do trading and stuff like that, like they're not into it, and they want to leave money somewhere for some number of years, and they want to get some percentage of it back. In that case, is not a good choice. Maybe if you want to do day trading or other stuff, maybe it works. And there are a lot of other applications for blockchain that some of it is like what you've some of you may have looked at, or I don't know if anyone is talking about voting, for example, e-vote, like electric voting or crypto voting is also like using similar concepts at the core of it. There are many concepts that are using nowadays like these decentralized things. And it's on hype, so a lot of these applications that we see out there are not valid, to be honest, I think. But over time, it's gonna become more mature, and people are gonna find the applications that are good and useful. I think that's pretty much it. So So you can read more about it. Any other questions? Yeah, any other questions? So let's have, and we're going to have another actually talk today about, I think, your group, right? Yeah. So you're gonna hear more about this, but yeah, I wanted to give you at least the basics of like what a smart contract is, what a forking concept, and some of these basic concepts in simple words, so that when you hear it, you can actually go and read it yourself.